Okay, Unit 1-2 or Section 1-2 is a pretty big review from Algebra 2 on functions. So quickly let's define a function, and that is a relation that assigns to each element x. Let's see, to each element, instead of x and y, I'm going to say to each element in the domain exactly one element in the range. So we can define domain and range. We could say the domain is the set of inputs and then sometimes you'll hear me refer to those as independent variables. And then very often that's x, and then the range is the set of outputs. And those are going to be the dependent variables, which is y, or since we're talking about functions, we'll say that's f of x, g of x. So the independent variable we'll just say, we'll call that x. It doesn't depend on anything. A lot of times that's going to be something like time, where time marches on whether or not anything's going on in our function. The dependent variable very often is the y, and that, depending which value of the dependent variable you pick, it's going to matter where that ends up on the function. And we'll just call that the output. So, a rule of correspondence that matches the quantities from one set with items from a different set, we'll call that well, is it a relation? Is it a function? I'm not 100% sure what they're looking for here. I'm going to call that a relation, because we're not being quite specific to say whether it's exactly one. In functions that can be represented by ordered pairs, the first coordinate in each ordered pair is the domain, and the second is the range. Some characteristics of a function from set A to set B. So each element of A must be matched with an element of B. And you don't have to watch me copy these. I'll pause here and you can get them, you can pause as well. Okay, so number 2, some elements of B may not be matched with any element of A. Part 3, 2 or more elements of A may be matched with the same element of B. And number 4, an element of A or the domain may not be matched with more than one element of B, and that's the range. So to determine whether or not a relation is a function, you must decide whether each input value is matched with exactly one output value. So we're going to see some examples of that in just a moment. So if any input value of a relation is matched with two or more output values, then the relation is not a function. So some common ways to represent functions are with a table, ordered pairs, a graph, or function notation. And you'll hear me call that the rule of 4. There's always 4 ways to represent any function, whether it's a line, a parabola, any of the function shapes we're going to be learning about this year. So we're going to take a look at the table in example 1 and determine whether or not it represents a function. So I'm taking a look at my domain, and just for funsies, I'm going to represent it as a mapping. So I'm going to list the items in my domain, and I'm going to list the items in my range. And so -3 maps with 5. -1 maps with -12. Oopsie, I shouldn't have listed 5 twice because 0 maps with 5 as well. 2 maps with 3, 4 maps with 14. So it's okay that more than one item in A maps with 5. The key is that there's just one arrow coming out of each item in the domain. So the answer, decide whether it's a function, that would be yes, that's a function. One of the ways that we can show functions is using function notation, and that's the symbol f of x, and that's function notation for the value of f at x, where we say f of x. The symbol f of x corresponds to the I could say the y value here, I could say the output. Keep in mind that f is the name of the function, whereas f of x is the output value. In function notation, the x is the independent variable, and the f of x is the dependent variable. Okay, so in example 2, we're going to take a look at f of w. F of w equals 4w cubed minus 5w squared minus 7w plus 13. Describe how to find f of -2. So, in using function notation, we're going to replace the w with a -2. So sometimes you'll hear me refer to that as erase and replace. So we are literally going to go through, and wherever we see a w, we are going to erase the w and replace it with whatever f value you've been given. So in this case, you've been given a -2. So I'm going to rewrite the function, but instead of a w, going to replace that with a -2. And whenever I replace, I always want to use parentheses. That way I'm not going to mess up any values with taking a negative to an exponent. So -5 times -2 squared minus 7 times -2 plus 13. And then I'm going to evaluate this function for those values. So I'm using the order of operations, so I'm working out my exponents first. -2 to the third power is equivalent to -8. -5 times -2 squared is +4. -7 times -2, so that's a multiplication, but I will go ahead and wait until my next step to do that. So because I multiply from left to right in the order of operations, so -32 minus 20 plus 14 plus 13. And now I can add or subtract from left to right. -32 minus 20 is -52. -52 plus 14. Let me just move over here. -52 plus 14. So I have to do 52 minus 14 is... Okay, it's way too early. So let me grab my calculator at this point. Alright, -52 plus 14 plus 13, -25. So next in our notes we come to something called a piecewise defined function. And so I'm going to define that. It's defined by two or more equations over a specified domain. Now we're going to have a whole separate set of notes that we're going to work on together about piecewise functions. So we are going to look at some of those later. Now let's talk more specifically about domains and implied domains. The implied domain of a function given defined by an algebraic expression is the set of all real numbers for which the expression is defined. So we're going to practice pretty much all semester long how to find domains of functions. But in general, the domain of a function excludes values that result in division by 0, or taking the even root of a negative. So the implied domain of this function is all reals. And then what value would make this whole thing become negative? Well, I could see where would it equal 0, and then add 8 and divide by 5. So when x is 8/5, this thing equals 0. So I can take the square root of 8/5, but what I can't do is take the square root of anything less than that. So we've got to be greater than or equal to 8/5, and then, so that's one way to write our domain, but really we want to start with interval notation. So at 8/5 we have kind of a hard stop here, and then we can go all the way up to positive infinity. And so this interval notation is going to be the best way for you to write domains and ranges. So on page 22 we start applications of functions, so let's just see what we have here. The price P in dollars of a child's handmade sweater is given by the function P of S equals 3S plus 15, where S represents the size of the sweater. Use this function to find the price of a child's size 5 handmade sweater. So P of S is 3S plus 15, and I'm looking for, okay, that's my letter S. You'll never see me using an S if I'm in charge of choosing the variables because it looks so much like a 5. So I'm going to substitute 5, so I'm going to erase the S's and replace them with 5s. So I work out the math in order of operation, so 3 times 5 is 15, plus 15 equals 30. On page 23 we start getting into something called a difference quotient, and I'll define it here, but we have a whole separate lesson on difference quotients because they're so important as getting ready for calculus. So a difference quotient is defined as the ratio between f of x plus h, and then I'm going to subtract out f of x, and I'm going to divide all of that by h. So I'm not sure if you've ever seen one of those before. That is kind of the fundamental basis of calculus, making an incremental change to something and seeing how that affects the entire operation. We are going to do lots and lots of notes and examples on those in a separate video and in class. So describe a real-life situation which can be represented by a function. We'll talk about that in class. So that concludes our notes for this unit. Can't tell if that was in the video or not, but you should have that written down as your definition of a difference quotient, and the rest will come later.